This is your mini lesson for chapter 1, section 2, displaying quantitative data in graphs. So first we'll lay out the objectives. We're going to develop academic vocabulary needed to describe the shape, outliers, center, and spread of a distribution of quantitative data. So since we're talking quantitative data, it's going to be numbers, and it's going to be a visualization of a set of numbers, and we'll have those four things we want to describe. Now that's going to be the first use of acronyms in this class. Acronyms are very helpful in basically trying to meet the bar set by AP graders. There's four things you should describe when you're describing a distribution, and that's going to be this SOX acronym: shape, outliers, center, and spread. We're going to learn to distinguish between continuous and discrete quantitative variables. So there's two types of quantitative variables. Both are numbers, but there's something different about continuous versus discrete. We're going to make and interpret dot plots, which we've already done, and stem plots. And then we're going to make and interpret histograms of quantitative data also. And then we'll learn to compare distributions. So first of all, let's talk about this phrase, describe a distribution. So classically on the AP exam, at some point you'll be asked to describe a distribution. And the graders basically all agree that those four things, shape, outliers, center, and spread, SOX, is an important piece. Next thing is, just in statistics in general, it's safest to use LY words. So it's a little bit of a hedge. It's a little bit of a honest approach with whoever's reading your work. We're not saying it's symmetric. We're saying it's approximately symmetric. So approximate, roughly, moderately, or slightly. And then you kind of realize that approximately and roughly are really just generally approximating, and then moderately and slightly and strongly, those are starting to kind of still approximate, but giving you which end of the continuum they're on. Those are all possible ways to kind of hedge your language. And then, like I said, describe these four characteristics. So in shape, I'm going to give you three words you can use along with these LY words to describe the shape of a distribution. And the first one is uniform. So I think you guys know that word well enough that if I was asking the class, which of the three distributions that we did when we were building, when we were collecting the data, which one of those, the dice rolling, the timer, or how far away have you traveled, which one seems most uniform? And because when you roll die, you have an equal opportunity to roll a 1, a 2, a 3, or 4, or 5, or 6, you end up with a relatively uniform distribution eventually. It may not happen over the short term, but over the long term, that would be what a uniform distribution looks like. Now, a symmetric distribution doesn't need to be uniform. It can be. Symmetric is a word that you could describe uniform with, but the bigger story is uniform. But this is an example of a symmetric distribution where, if you basically fold it in half, it's generally symmetric. It's generally the left and the right mirror each other. That versus a skewed set of data. And this is an example of a skewed set of data. And I want to warn you that the word skewed is used pretty much incorrectly, I'd say, more times than not in the real world. And I was guilty of it myself. If I was going to tell people, yeah, I go to a gym and it's a good place for me to go because, we kind of skew to the older side of the population. You might think, oh, so he's saying that there's a lot more older people there than there are young 20-somethings working out. And it's actually a little incorrect. Skewed, things are skewed in the direction of the tail. So this is data that we may have just collected on distances, and it's skewed to the right. And the idea there is if we were to give you an average, a mean of those distances, you would get a number that is probably highly influenced by this point right here. So if we gave you an average number and it was a number, we said the average of all these numbers was like here or something like that, it's because this guy is getting weighted, so is weighting things so heavily, not because there's so many that are in that area. So the short story is, when we say skewed right, the tail goes to the right. If it was skewed left, it would look more like this, where there's a tail on the left and then on the right-hand side. And it certainly would not be symmetric. One more thing that we can do to describe shape, we can talk about the modes. This is unimodal because there's kind of one peak. It's not bimodal or multimodal, but those are words you could also try to use to help yourself describe the shape of a distribution. So that's one of four. And that's pretty involved. The good news is these other ones are going to be a little quicker for right now. So outliers are points that seem separated from the vast majority of points. And right now, we did already experience a data set where there was an outlier. And that would probably be, if I were to ask that question, which of the ones we did were had an outlier, we'd say there was probably this distance one right here, because there was there was someone in one of our classes that I worked with who visited a very, very far away place versus these other people who would went within a few hundred miles of Glen Mills. But for now, along with that definition, we're just going to use the phrase like that. There's apparent outliers, or we're going to mention there are no outliers. We're not going to use specific work to figure out which one's an outlier and which one's not. That'll change down the line. So these two we could say are apparent outliers in that distribution. The center, again, for now, we're just going to use approximate. We're going to kind of try to find the center of the distribution visually. So I'd say those 3 points right there. Notice in this case, again, we don't want to say the mean, which would be highly influenced by these things right here. And so it's really a median when I say we're trying to find the center for now. And that's going to be hashed out a little bit more clearly later. We're going to tell people specifically whether we're talking about the mean or the median when we talk about a center. But for now, we're going to say it's centered at approximately 3 or 4 for the dice rolling, and it's centered at approximately 5 seconds for the stopwatch. And for spread, there's going to be 2 ways we're going to phrase that for now. We're either going to say it varies from blank to blank, and we'll say the low and the high values, or we might give the range. And the range is not the same thing as a span. An example would be the stopwatch times varied from 4.63 seconds to 5.42. That's a good way to describe the spread. And you could use that same information to say it differently. That you could say the stopwatch times had a range of 0.79 seconds, and that's the difference between these two numbers here. So those are your choices on how to describe the spread. So at this point, we've given you some vocabulary and some ideas of how you're going to describe those 4 important characteristics of a distribution. Moving on, let's talk about continuous and discrete. This will be a little bit quicker. Continuous numeric data, it's usually a count. But in general, it's any numeric data where there are gaps. Whoops, I'm sorry, that's the definition for discrete. And I think I do change that later on in the slides. So I'm sorry about that. Discrete data has gaps between possible values. So if I ask the question, which of the 3 distributions that we built today were discrete data where there were gaps between the values we got, and there had to be gaps between the values, that would have been the dice rolling. So the result of the dice could be a 1, a 2, or 3. It could not be a 3.1. It could not be a 3.05. So there are going to be gaps between the possible values. That's what discrete means. A lot of times you also are able to count, as I said before. Now continuous, as the name implies, there's this kind of steady flow between one possible value and the next possible value. So a lot of times it ends up being a measurement instead of a count. And it's numeric data where any value in a given interval is possible. So decimals and fractions are usually features of kind of giveaways. There's continuous data. Like time is measured, and you could have, milliseconds between things. Distance, same thing. So let's quickly talk about an interesting example, shoe size. So shoe size is worth talking about in terms of discrete or continuous, because I think that people could give an argument for either. Someone could probably look at the evidence and they could say, hey, this is what's making me say shoe size is discrete. And I'm wondering if anyone could think about that. And that would be the person who says there's size 5, there's size 5.5, there's size 6, there's certain values that you can take, and there's no values in between. Even if someone's foot is a different size in between, the shoe size is not. The argument that it's continuous would be, well, your shoe size is a measurement, but those people would be a little bit misleaded. Those people are overusing the idea of count versus measure. So you really need to be thinking about what are the true possible values you can have, and if there's gaps where there's no way that it could take on a value in between certain gaps, even if there are gaps between halves, that's going to be discrete, versus if there are no gaps, that's going to be continuous. So ultimately, shoe size, as we said, is discrete despite the half values that are in there. So in order to hit this last 2 objectives, make and interpret dot plots and stem plots, and make and interpret histograms, I'm just going to put forth a couple examples of these things, and I'm going to talk about some tips, and then I'm going to set you loose on some work with stem plots and histograms. And you'll be doing this in groups, and you'll possibly struggle a little bit, but that's a more active way than just sitting here listening to these notes. So first of all, this is what a stem plot looks like, and they are called stem and leaf plots, and they are earlier in the middle school curriculum. But the idea is if you have a set of data that includes 4 and 6 and 12 and 14 and 18, you could represent it that way. And a good stem plot is going to have the lead digit and then any value that has that as the lead digit, it's going to be they're going to be represented by kind of just the rest of the number. And notice that it's not a coincidence that these are in order. A bad stem plot would have 3, 4, and then the 5, 5, 7, 8, and then the last 4 over here. You want to have these things in order, and that's because if we want to find a median or something like that, that becomes helpful. A good stem plot also has a key down here. Now you notice that there's other types of stem plots. Splitting stems is something that could happen if you had large numbers of items that were in each category. Then splitting stems might make it a little bit more visually appealing. So you can see this one was split where 20 through 24, those 5 possible values were listed here, and then 25 through 29 were listed here. And once again, they are in order. And then the other thing that could happen is if you have 2 different distributions and you're trying to represent them both in stem plots, you could use side-by-side stem plots instead. So in this case, you had before and you had after, and like an 86 was a after measurement and an 82 was a before measurement. So you notice that the order of the numbers grows from low to high on the right-hand side, and then from low to high working from the inside out. So that's what you would do for a side stem plot if you're trying to show 2 different distributions of the same stem plot. Just some pointers out of your textbook. Stem plots should not be used for really large data sets. It's not really as telling when you do that. If each stem holds a lot of data, like I said, the visual becomes pretty confusing. There's no magic number of stems. So if you're choosing on whether you want to split or not, there is no magic number, but 5 is usually about as low as you're going to go. If you split stems, be consistent with leading digits across them. And what they mean by that is this. If you're going to go 25 through 29, then you need to go 35 through 39 down the line. And the other thing is, even if there's no data in something, like if we had, if we have here, there's no 20, there's no 20, there's no 21, there's nothing up to 29, but they still included that. So you can see the gap. And if we were doing split stems, if there were no 35s through 39s here, you would still want to use the split stem for 3. It would be consistent. And rounding is a helpful tool. And the reason rounding is a helpful tool, all these stem plots are just trying to give you a visual. And if you look at this little middle example real fast, what it's trying to do is it's trying to basically give you a bar graph or a histogram that helps you see this. So rounding, it didn't matter whether this was 35.1 or 35.13. 35 was good enough to let you see that there were, 8 entries in this column and only 3 entries in this column. So rounding is helpful. Histograms, this is what a histogram is. You've seen them plenty of times before. They look a lot like a bar chart, but it's numeric data. So what you do is you kind of have no gaps between the bars because they're not different categories that are separate from each other. They're intervals that flow into each other. Now, because they do flow into each other, you want to be careful about how you label these things. You want to be clear about it. This is a great way to label these categories. They found 5 instances of numbers between 62 and 64. Now, it might be confusing because the 62 and 62, I think this is a little bit weak because we don't know if I came up with a 62, which bar would grow. Would the 60 to 62 bar grow, or would the 62 to 64 bar grow? So another way that you might approach it, I'll show you in a second. But histograms, what it tries to do is it tries to make groups out of values and ranges of quantitative variables. There's no set number of bins, same thing. Try to go between 5 and 15, they said. And then the way you find the size of a bin is you take your highest value in your list, you subtract your lowest value, and you divide by the number of bins that you're looking for. This is a really, really nice way to show your ranges. 20 says that if you have a 20, you know it's going to be represented in this bar. And then less than 25 is telling you 24, 24.8, 24.99. They would also go into this bar, but now 25 would be in this one. So using those less than signs is not a bad idea when you're laying out your bins. So at this point, you'll have a couple problems to work on. One's going to involve stem plots and one's going to involve histograms, and you're going to get a chance to probably deepen your learning a little bit on these things.